Okay, I would like to go back to the lecture. And so far I showed you some examples for the importance of particle size distributions. I hope it was not too much, but in my opinion it's very, very important because the theory is not that problematic, it's quite simple. And it's for me important to understand that there's really an application of this knowledge about nanoparticle sizes, size distribution. And this is why I want to show you these different examples. So when it comes to describing the sizes, the easiest way is to talk about a mean value, right? So we have distributed sizes as in this class, and an average, I say, okay, the average height in this class is 1.76, okay? And then we have a standard deviation, and then it's very, very simple to describe. And therefore, we have to make some assumption, and one of the most simple assumption we can do when it comes also to mathematical description is the shape, right? Because for liquids, it's very simple. If we have droplets, what is the shape of a droplet, roughly? A sphere, right? A droplet is always a sphere, okay? Or mostly, a rain droplet not perfectly, but it's very, very simple. But how about solid particles? Are they always spherical? All right. But what can we assume to keep our life simple? Yeah? Yeah, we assume they're a sphere. And for a lot of them, it works quite good. Some of them are not perfectly a sphere, but then there's something like a correction factor, and some of them are like fibers, and then we would calculate with a fiber. Okay, a fiber is also a cylinder, for example. So a sphere is a very, very good assumption, very often assumption, and later we'll get to know much more complex shapes, and then there are different ways how to describe it. One word you already keep in mind is fractal dimension, okay? So, quite simple, but what is the volume of a sphere? How can we describe or how can we calculate the volume of a sphere? 4 divided by 3 pi r cubed. Okay, and this is based on which variable? Radius, exactly. So, I don't know where's the middle, somewhere here is the middle. Radius. What else? We can describe also the volume by a different entity. It's quite simple math, but it's, yeah, by diameter. What happens to this equation then? Again? Exactly. And please keep these two in mind, because in literature and whatever, you not always know if you have diameter or if you have radius. And we have equations later where we need to put in the radius or the diameter, and we make this assumption, and then we will reshape it and calculate with it. And of course, the outcome of the equation is different if you put this in or if you put this in, okay? And normally we talk about diameter. And comes, but always be very, very careful when you see these diagrams and there's particle size, keep in mind, okay, is it radius, is it diameter, or is it at the end doesn't matter? Because I just look at the diagram and there's a factor of 2, but if you put it into equations, there will be a difference, okay? So please keep this in mind, just to make the picture complete. What is about the area, the cross-sectional area for radius? Yeah? Pi r square. It's correct? Yeah? It's not a problem, it's fine. I do this all the time. So it is? 4, right? And what happens then for here? Yeah? Yeah, pi d squared. So a small reminder, but please keep this in mind, okay? Can become important. So this assumption also is important because we use to describe a diameter by equivalent diameters. What is an equivalent diameter? So I measure an aerosol particle with a weird shape, this kind of shape, whatever. They have these kind of shapes. And I would like to describe it because it's easier to calculate with this than with this. So what is an equivalent diameter? Yeah? Exactly. So you would say, okay, my weird key particle has this sinking speed, and a sphere with a given diameter has the same one. So I can describe it by the diameter of the sphere having the same settling behavior. Okay? And here are a few of these diameters, and I just want to point out before. So an equivalent diameter, and now I just read it because I don't want to make a mistake, is the diameter of a sphere, is a diameter of a sphere having the same particular, I guess, yeah, having the same value of a particular physical property. Having the same value of a particular physical property. Now it's a little bit as the irregular particle. Right? The key is the irregular particle. And an equivalent diameter is a diameter of a sphere. So there is an imaginary sphere which has the same physical property than my key, for example, in falling down. And the diameter of this sphere is the one I get out of my measuring device. And by this, I describe this size, okay? And we have here different diameters. So the Stokes diameter is what you describe. The Stokes diameter is the diameter of a sphere with the same sedimentation velocity in Stokes regime, so laminar flow. And this is quite simple to measure. There's something called Andreasen pipette. And then you just need a very dilute system, right? The particles should not be too close to each other because that would give different behavior. And in this way, you can measure between 2 to 100 microns, very precise sizes. That's quite, well, it's okay. And there is a more advanced system, and this is a centrifuge. So if you have a centrifuge, you can go, I think, down to 10 nanometer or something, and you use the same, you get at the end a Stokes diameter of the traveling particle. So a centrifuge is increasing gravity, and by this you're measuring the behavior through a liquid, and there you can, so the size distribution from centrifuge, where you put particles in a liquid, will give you this Stokes diameter. Then there is the aerodynamic diameter, and the aerodynamic diameter is quite important when it comes to health. Okay, it's the movement of aerosols, or the movement behavior. There's, for example, a cascade impactor, which is measuring these devices. It's like a sieving tower, but with a different working principle, you go to lower sizes. And you see the definition: diameter of a sphere with a density of 1 gram per cubic centimeter having the same sedimentation velocity. So the density of the sphere is defined different than in the Stokes diameter, and this aerodynamic diameter is very often used when it comes to health issues, right? PM10, PM2.5 is related to the aerodynamic diameter. And of course, the diameters can be different, okay? So you have the same powder, but you get different size distribution depending on what you're measuring. So we have the mobility diameter. The mobility diameter means you have an aerosol, and you're charging the aerosol, okay? So it goes somewhere through an area where you have a lot of ions. The ions go to the surface of the particle is charged, and then these charged particles, they go into a chamber with an electric field. And based on the behavior in the electric field, you can take their size. So what you basically do, and that's quite nice, is you make a force balance. Drag equals Fe is electric force. And when you calculate a little bit, you get something called mobility. And the mobility is the ratio of the velocity of the particle in the electric field as a ratio to the strength of the electric field. Okay? And from there, you can say something about the size. So, and the last one is optical diameter, and this is very, very often used in industry because it's a very simple method. You have a laser, 630 nanometer wavelength, and then you go with the aerosol, the laser, and the reflection tells you something about the size. So there's Mies scattering, Rayleigh scattering, and these things. And in this way, you can very, very easily measure and effectively measure particle sizes. Okay, different methods for different applications, more or less expensive. It really depends what you want, but please keep in mind if you read diameter somewhere, what kind of diameter, how is it measured, is it important that it's measured by this way or not, okay? Sometimes you get information from a completely wrong diameter, which is not related to your use case, okay? And then you have to be a little bit careful. And this is also what you see here, so be careful with the interpretation. So these are computer simulations, and these 3 particles have the same mobility diameter, okay? So here you see now the picture of an equivalent. So this would be the real particle coming out of a flame process, for example. Carbon black looks like this. And this is how it looks in the equivalent diameter, okay? And this means they 3 have the same mobility diameter. They're the same if you look through these glasses. But if you look for mass, they're completely different. This one has a much, much higher mass than this one. But you don't measure by mass here, okay? And also for surface area, this one has a much, much higher surface area than this one, but you don't measure for surface area here, okay? And I think I really like this image because it really shows how important the choosing the right value can be and what kind of difference it has, and really what an equivalent diameter is. Okay, aerosol concentration is something which is important when it comes to health, to see, right? So smoke, cigarette smoke, and so on. And here's just a diagram where you get a little bit an idea about concentrations, but you keep in mind these 10,000 particles per cubic centimeter. And here you have polluted air. This is background aerosol. Here's about meter, so keep care. So from here to here means, okay, you have very polluted air. This is if you are in an aerosol reactor, so never put your head into an aerosol reactor. It's not very healthy. And this is what you have to go to get a class 1 clean room. So this is why the clean rooms are so expensive, and the people always cover all these things, because what you do is you decrease the background aerosols, okay? So this is the step you go to the clean room. Do you know one application where a clean room is extremely important? We will talk about this in one of the transport lectures. Yeah? Yeah, for computer chips, right? Silicon and yeah. There are clean rooms extremely expensive. So, and to give you a little bit more feeling about aerosol concentration, I have an example for you. You have to calculate a little bit. So, you see my brother-in-law who's smoking. And smoking a one non-filter cigarette, there is something about the filter in a cigarette. Okay, we will learn about this also later. But in smoking one non-filter cigarette, a person inhales 350 milliliter of aerosol containing 20 milligram of tobacco smoke particles. If these particles are standard density, 1000 kilogram per cubic meter, spheres of dp in diameter 400 nanometer, calculate how many particles does the smoker inhale from one cigarette, what is the mass concentration of the smoke, and make a ratio or comparison of this smoke concentration to the US PM10 standard of 40 microgram per cubic meter. So I want you to make the calculations now. It's very simple calculations, but in my opinion, it's a quite nice example to understand a little bit. Okay, so you have some numbers, right? So a person inhales 350 milliliter. So when you're smoking, you inhale, and in these 350 milliliters are 20 milligrams of particles, just by weight, okay? So if you smoke, you inhale 20 milligrams. And these particles have a density and a size. And these are the four informations you have. And with these four information, I would like to know what is the mass concentration of the smoke, okay? And how many particles are this? Because there's nothing about the number. It's just a weight. So I would like to have the number of particles. And then we could make a ratio comparison to the PM10 standard, which is the standard where you say don't inhale more than this amount of particles. Okay. It's now more clear or? Okay. Okay, due to time, I just run around as you see. And due to time, I would like to skip a little bit, or not a little bit, I don't know if you can skip a little bit, to skip. And I would ask you to do this as a homework, okay? So I would like ask you to calculate this till we see us the next time, okay? Take your time, because it's quite simple calculation. I'm sure you are able to do it. But it's for me important to, I mean, we could do the calculation now on the board, and actually it was what I planned first, but now I'm thinking it's maybe better. Take your time and make these calculations. If you have problems with these calculations, please let me know, okay? It's for me important to see a little bit the adjustment. And I think it's more valuable for you to take 20 minutes and make the calculations, and I will give you, when we start the next lecture, we will make the solution of this, okay? So take it as a homework with you. Any questions to it? I will upload it anyway, okay? But before I just put the solution on here, I would like to see or give you the chance to take a few minutes more on it, okay? And we cannot deliver it in the class. Okay. What do we calculate here? We calculate the amount of particles a smoker inhales. I already can tell you it will be something with 10 to the power 11, the numbers, okay? You can keep this as a mark for your homework, 10 to the power 11. Should be something for the number of particles. And that's quite a lot, right? So 10 to the power 11. And when it comes to the comparison, it's 10 to the power 6 more than you should, based to PM10 standard. Okay, but this is an average value over, I think, over the year, the 40 microns. For 24 hours, the number is higher. You can be exposed for 24 hours to more. But as a smoker, you inhale 10 to the power 6 more particles than you should compared to the regulation. I don't know if anybody is smoking. You don't have to show up. I was smoking in the past. I don't smoke anymore. But of course, we do a lot of oversimplifications here. We just calculate with average numbers, okay? And average numbers are these numbers here. And you have to be very careful because normally particles are size distributed. Okay, and this means you have a size distribution, and remind the example with millimeter, meter, and kilometer. And the numbers we have here in the exercise are just one number out of the size distribution. And depending on the shape of the size distribution, the meaning of your number could be different. So it's different if you have the mode. What is the mode of a distribution? It's a statistical value. What is the mode? Yeah? Yeah, highest frequency. So if you have a number of sizes and you put them in boxes, the box with the most numbers in there, this would be the mode, so the maximum of the size distribution. What is the median of a size distribution? That's here, median diameter. What is the median? Yeah?
50% is above
yeah.
value and 50% below.
Yeah, 50% is below the median and 50% is above. So the median is the value directly cutting your distribution. And what is the arithmetic mean? The average? Mm-hmm. So exactly, it's all summed up, divided by the number you have. And all three, that's important because the arithmetic mean is normally the average value we talk about. But all three are average value: mode, mean, and arithmetic mean. Mode, median, and arithmetic mean, sorry. What is in a standard deviated distribution? What is with these three values? If you just have standard deviation, a normal Gauss distribution. What is with these three values? Yeah, it's average, that's right, but what is the property of these three average values in a normal distribution? Yeah?
They should be the same.
They should be the same, exactly. So if we have a normal distribution and the height here in this class would be normal distributed, so it doesn't matter if I take mode, mean, or median. It's always the same. Particle sizes are not really normal distributed, okay? Mostly, as you see here, log norm distributed. And in a log norm distribution, it's a big difference if you have the mode, the median, or the mean. Okay, so if we talk about these diameters here, and you will have a mean, an average diameter, you have to be sure, okay, what average diameter do I have? And normally, the one we take with a log normal distribution is the median, okay? The median value and the geometric standard deviation is what you need to describe a log normal distribution. And aerosol particles, general particles, are mainly log norm distributed. So if I would have a cup here and I crush the cup, the size of the Scherben, what is Scherben? Crushing pieces of the pieces, would be log norm. The moons around planets in sizes are log norm, okay? So particles are log norm distributed. And this is why we have to deal with distributions. And there is a very simple way, and this is what I want to go through here, is in particle technology, we do it a little bit more extensive. So it's a test aerosol. I think this one was, if I remind right, it was a mobility diameter here, or aerodynamic, I have to look it up. Aerodynamic or mobility diameter was measured. And so you have your measuring device. Let's say it's mobility diameter, so electric field measurement, and then you get these numbers. So you count here, okay, so you have 104 particles in the size range 0 to 4. And you have 160 particles 4 to 6 microns. And by some weird coincidence, we directly have 1,000 particles. You can imagine if this is a real measurement or if these are random values. But here something already happened, and this is the grouping. Okay, so you already divide boxes. Okay, box number 1, put these in. Box number 2, put these in, okay? Then you can make some simple calculations. So you can have the fraction in microns, and you have the percentage. And the percentage is quite easy. So we have 1,000 particles, 104 are here, so 10.4% are here. So this is the amount in percentage in each box, and this is the cumulative percentage. So what are you doing in this row? What happens here in this row? Difference to this one? Yeah? Yeah. So you're just starting from the lowest one, and then you're just adding. Okay, this is a simple table. And with this table, we already can do a few things. And the first one is we just can plot these two lines or rows here. And then we would get this diagram. It's a histogram. But we have to be very careful because this is just a representation of the data. So there is the particle diameter, okay? Similar as in the examples with the lipid nanoparticles and so on. And here's the frequency, and the frequency is just the number, okay? How many are in the box? 104 or whatever. So, but you see that these numbers here, so here would be 104, for example. So why I have to be very careful with this diagram here? To what is it very sensitive? Or is it now size distribution and I can present it in a paper or in a master thesis? What happens if, for example, I change the numbers here and put both of them together to one interval? So this is one interval with 80 and this is one interval with 90 or 100. So let's say I say, okay, it's not between 16 and 20 and 20 and 35, but it's between 60 and 35 is the interval where I put all my, so I put two boxes to one. What directly happens with this area? It gets bigger, right? So by a quite simple trick, I could say, oh, most of the particles are here. They are larger than 15 microns or whatever. Most of them are here. Okay, because it's just the amount of number and some randomly chosen intervals. And how I choose the intervals, I can play around with the height of the bar there. And in this way, I very easy can manipulate the diagram. So you have to be very, very careful. How can I avoid this? I can make a very simple trick by avoiding this problem. What could I do that it doesn't matter how large the interval is? So I have a small interval and I have a large interval. Since this is larger in size, I have more particles. How could I make these two comparable?
Dividing range?
Yeah, dividing by, so if I divide this by this and this by this, I cannot play around with these tricks, right? And if I do this with this data, if I just divide it by the length of the interval, it changes, okay? So same data, and now we get an idea that we don't have many particles here. It's just a long interval we choose, okay? And all of the particles are here, and we see here these two jump up now because the interval is very small, okay? So it's a complete difference from left to right. And this is because on the right one, we divide by the length of the interval, we're kind of normalizing it, that we make it comparable, okay? But we are still not finished, and one thing is still problematic here, and this is the y-axis. So now I can compare everything within this diagram, but it's hard to compare it to another diagram. Because if I take this diagram, and in this case, I measured 1,000 particles. And this is also seen on my y-axis. So if I would make a distribution out of it, I want to have it at least log norm. And now I don't measure 1,000, but 100,000 particles. So this means I get a distribution like this. Could I compare both of them? What can I do to make them comparable? Yeah? Yeah, use the frequency as a percentage, and how do I do it? It's again a very simple step.
Dividing by the sum.
Exactly, divided by the whole amount of particles, or the total mass of all my particles, or whatever you are measuring. So one is you're measuring, and then you have to consider the length of your interval to make everything in your diagram comparable. And then you have to divide by the amount of overall particles, and this would put them together. And here is now, I think, this is from here to here. So this is what you see on the y-axis. By 1,000, it's quite easy, right? So you see the 1,000 directly here. But here it's the frequency, and the frequency is the number, the amount divided by micrometer, and the divided by micrometer is this one. And now we call this one, now the frequency, we make out of the frequency the fraction, and this would mean the amount of particles divided by all particles, okay? And then we can make them comparable. And if you make more and more bars, or you change the bars into points and make a fitting, then you get a size distribution, okay? And this size distribution, what you see here is the probability density function. It's something you know from statistics, but it's important that you always have to be correct in the depiction of this. And correct means not just measure the data here and just plot x over y, take the first two rows, x over y, and say, that's my particle size distribution, okay? It's somehow a particle size distribution, but it's not a probability density function. And only with a probability density function you can avoid this problem, and you can compare different measurements to each other, okay? That's the important thing. What is a directly outcome of the probability density function? There's a property where you can be very sure if this property is there, I have a correct probability density function. What is a property of this function? I'm sure you know this. What is if I take the integral out of this function? Yeah? What happens then? Yeah? Mm-hmm. Very good. So what you can do is you integrate this function. Okay, you make an integral out of this function. And if you do so, you get this. And this is the cumulative size distribution. And the cumulative size distribution is what you see here. Okay? So if you take this data and you reshape it to a correct probability density function, and you could check the ones I showed you in the examples if they are really probability density function or not, and you make the integral out of it, you get a cumulative fraction, and the cumulative fraction goes from 0 to 1. So 1 would be 100%. And if your cumulative size distribution goes from 0 to 1, the area under your probability density function has to be 1. And if the area below this curve is 1, everything is fine. And very often, you can directly make a guess if the 1 fits or not. Okay, because we have 10 and we have 0.08. And then you say, okay, and you have 30 and you have 0.005 or whatever this is, okay? And there you directly can see if you're in the correct size range, okay? Because if you make an error, you will directly see that, okay, 80 and 10 cannot be below 1, right? 80 and 10 is already, or here would be 10 and 50, it's already more than 1, cannot be correct. So very, very simple. And the other way, if you have the cumulative fraction, or the cumulative size distribution, how do I get the probability density function? the other way around, yeah? Derive it, right? So if you have the cumulative size distribution, you can make a derivation and you get the probability density. If you have the probability density, you make the integral and you get the cumulative one. For the cacao example, we had both, but you could calculate one of the other, and mainly the system is measuring one and just gives you the other. And this is, in particle technology, you also have to make a Python script, and it's quite simple to do the Python script, right? You should say. No, but let's say it in this way. It's a very good way to learn Python. I think therefore the task is quite good because you do it step by step and you can try it with the data from the diagram, from the table. Just try to make a small Python diagram or try to generate these. If you have this once, you can use this for all time. And we actually get approaches from companies to do just the calculations for them, okay? Because they say, okay, we basically know it, but it's 10 years away, and it's easier to give you money to do it instead of go to that. So it's worth to do these things, okay? Yeah. Any questions to this? Okay, so one thing you have to really, really consider is this diagram. What is the meaning of this one? And then we are more or less done and can go into the lunch break. What do you see here? Mm-hmm. Exactly. So this is not two different samples. This is the same sample, okay? But it's measured by number or by mass. By number means you just count, right? 1, 2, 3, 4, 5, 6, 7. And normally, if a distribution is log norm distributed, it means I have more small or less small particles by number. For a log norm distribution, by number, do I have more small or more large particles? Just remind the diagram before. Yeah, so in a log norm distribution by number, you have a lot of small particles. That's the characteristic of log norm, and not so many big guys. However, if you think about it, counting, okay. But if you think about weight, that means you have one big guy and you put him on the balance. And for the one big guy counts this to the cube. And you have a lot of small ones and you put them on the balance, the same obeys, right? And this means you don't see them, okay? And this means the same sample could give a complete different distribution depending if you go towards mass or towards number. And in this way, if you want, you could hide a lot of small particles in your distribution, or you can pronounce them, okay? So again, keep this in mind, and keep in mind that if you have something where the number concentration is important because of the property or the product or whatever you want to do, then you need number. If the mass is important, number is not a good thing to measure because you get different distributions at the end. And there's also a quite complicated but fun way, and I would always like to have a project work on this. There is a way, so if you have log norm or if you have distributions, and that's the usage of it, if you have the mathematical distributions, you can describe them, okay? So if you have mean values, you can do calculation, and if you have distributions, you can do calculations. With this data, it's hard to do calculations. How do you describe this mathematically? You have to go to a fit to a distribution, and with the distribution, then you can calculate. And one thing you can do is you can do momentum calculation, so you calculate the statistical moments, and then you can calculate a number population into a mass population, okay? But this is a little bit more advanced. But I just want you to know that you can, if you measure this one, you fit a distribution through it, it's possible to calculate this one by the using of statistical moments. I don't know whom of you had statistical moments in statistic class. So it's nothing I mean, everybody knows what is a mean value, median value, and so on, but this is a little bit more detailed, and this is why I just want to touch it here. Okay, so To sum up, I hope you got a little bit an overview about the importance of size for aerosol technology. You have an idea about the technical applications. I really showed you some examples where you see, okay, the size is an important property and can make a difference. And yeah, nanotech was only touched in terms of nanoparticles today. And with this, I would like to end the class, and then we will go to lunch break and seminar. And with this, thank you.